In this video, we're going to be talking about summations and sigma notation. A summation, or sum for short, is when we add multiple things together. A convenient way to express a summation is by using the Greek letter sigma, and this specifically is a capital sigma. Let's define formally a summation. If a sub m plus 1, a sub m plus 2, a sub n minus 1, and a sub n are real numbers where m and n are integers such that m is less than or equal to n, then we say that the summation from I equals m to n of a sub I is equal to a sub m plus a sub m plus 1 plus a sub m plus 2 plus plus a sub n minus 1 plus a sub n. Now, in this graphic to the right, this thing is called the lower index, and then this thing is called the upper index. The lower index tells us where to start, and the upper index tells us where to end, and then the sigma is the symbol that tells us that we need to add, and then the thing that we're adding is the thing next to or to the right of our sigma symbol. Let's go ahead and jump into an example. Example 1 says, find the following summations. So here for part A, I have the summation from I equals 0 to 5 of I, and I'm going to go ahead and expand out this sum. So we start off with I equals 0, and then we're going to add our next term. So the next integer after 0 is 1. So I'm going to add 1, and then plus my next integer is 2, plus my next integer is 3, and I'm going to continue until I hit my upper index, which here is 5. So I want to go ahead and I want to add all of these values together. So 4 plus 5 is 9, 2 plus 3 is 5, and 0 plus 1 is 1, so I have 1 plus 5 plus 9, and if you add those together, that will give you 15. So our final answer for part A is 15. For part B, we have the summation from, now our index starts with k equals 1, and then ends at k equals 3, and we have k cubed. So this means that we are adding our first term is 1 cubed, plus 2 cubed, plus, and then our upper index is 3, so our last term for our summation is 3 cubed. This is equal to 1 plus 2 cubed is 8, and 3 cubed is 27. And if we simplify this, this ends up equaling 36. So our final answer for part B is 36. Okay, so for part C, we have the summation from I equals 1 to n of 4. Now notice that this does not have a variable in it. It's a constant. It's just 4, and our index is going to change from 1 to 2 to 3 all the way up to n, but the thing that we're adding is staying constant. So my first term is 4, my next term is 4, my next term is 4, and what happens is this is going to continue on until I add 4 one final time. So here, this is when my index is 1, this is when my index is 2, this is when my index is 3, and then this is when my index is n. And so what that means is there are n instances of the number 4. So if I'm adding 4 together n times, that is equivalent to 4 times n. So my final answer for part C is 4n. All right, let's move on to part D. Part D is actually a special summation, and you'll find later on that another word for a summation is a series. And this is a special kind of series. It is called a geometric series. So before we get to evaluating this specific geometric series, let's look at a more general geometric series. And I'm going to look at the summation starting at I equals 1 to n of some constant r to the ith power. So if I were to expand this, my first term would be r to the first power, my second term would be r squared, r cubed, and then my last term in my sum would be r to the nth power. So what I want to do is I'm going to call this sum here, I'm going to call this s sub n, and s stands for sum. So if s sub n is equal to that, then r times s sub n is, I'm going to take my summation and I'm just going to multiply every term by r. So my first term is r to the first power times r. If I simplified that, that would give me r squared. My next term, r squared times r, would give me r cubed. And then r to the fourth plus dot dot dot. And my very last term, what I would be doing is I'd be multiplying r to the power of n times r. So my final term would be r to the power of n plus 1. Now notice this here is equal to s sub n. And what if I wanted to subtract s sub n minus r times s sub n? So on the left-hand side, I have s sub n minus r times s sub n. What that means is we're essentially taking all of these terms and subtracting all of these terms here. So if I did that, what's going to end up happening is a lot of these terms are going to cancel out because r squared minus r squared is 0, r cubed minus r cubed is 0, and what's going to end up happening is my only two terms left are going to be r and r to the power of n plus 1. So what we're going to be left with is r minus r to the power of n plus 1. Now notice that on the left-hand side, I have s sub n in both terms. And if I factored that out, I would be left with 1 minus r. And my goal is to solve this for s sub n. And so if I divide both sides by 1 minus r, I get s sub n is equal to r minus r to the power of n plus 1 over 1 minus r. And so if I have, in general, a geometric series, this is what the sum is equal to. Okay, so we derived the formula for a geometric series if our lower index starts at 1 and our upper index starts at n, or ends at n. So now, how can we use this to help us answer part D? Well, part D, we have the summation from j equals 1 to n of 1/2 to the j power. So if I were to start to expand this out, this would be the same thing as 1/2 to the first power plus 1/2 to the second power plus 1/2 to the third power plus dot 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 plus, and then my last term would be, that should be a 2, 1/2 to the nth power. That would be my last term. And it turns out that there's actually a formula for this, and we can condense this looking back at our formula here. So R is the ratio that we're looking at. So in this case, our R is 1/2. That corresponds to this R here. So when we add up all of these terms together, we get 1/2 minus 1/2 to the n plus 1 power over 1 minus 1/2. And we can clean this up a bit. So in my denominator, 1 minus 1/2 is 1/2, and if I multiply by the reciprocal, I would have 2 over 1 times 1/2 minus 1/2 to the power of n plus 1. And if I distributed this, I would get 1 minus 2 times 1/2 to the n plus 1 power, like that. And so there is our final answer for part D. All right, the last part of this example, we want to move on to part E, and it's very similar to the one that we just did, except our lower index is starting at I equals 1, and our upper index ends at 10. And so if I were to expand this, now instead of stopping at n, my last term is 1/2 to the 10th power. And based on the formula that we just derived, we can figure out what that is equal to. So that's going to be equal to, I'm going to use this formula that we derived down here. So if I were to add up all of these terms together, then that would equal 1 minus 2 times 1/2 to the power of our upper index, which is 10, plus 1. So that's equal to 1 minus 2 times 1/2 to the 11th power. And if I exponentiated 1/2 and I combined that all into a single fraction, this would equal 1023 over 1024, which is approximately 0.99902. So that completes this example.